All right, so let's analyze the first derivative chart here. So if we start plugging in numbers again into our first derivative there, the denominator is going to be a positive always. But if I start plugging in numbers, so I'm going to skip through some of the details here, but plug in 1 and you'll get a positive result. Plug in 3, you'll get negative. Plug in 5, you'll get negative. Plug in 7 and you'll get positive. So we see that that means that f is increasing there, f is decreasing there, f is decreasing there, and f is increasing there. Okay, and that actually tells us that we have something going on at 2 and 6. So at 2, we have increasing and then decreasing. We topped out, that's a relative max at 2 something, and we bottomed out at 6, so a relative min at 6 something. And I would have to go back, so let me just do a little chart here. My x and y equals f of x. If we plug 2 and 6 into the original function, remember that's the x squared minus 6x plus 12 over x minus 4. You should get negative 2 at 2 and 6 at 6. So I get 2, negative 2, and 6, 6 as my rel max and rel min. So now let's move to the second derivative and look at inflection points, or look for some inflection points in concavity. All right, so I'm going to need the second derivative. So I would actually go back and use this form here in getting the second derivative. And so if I do that, I'm going to get, using quotient rule, 2x minus 8 times x minus 4 squared minus x squared minus 8x plus 12 times 2 times x minus 4 from the chain rule over x minus 4 all squared. All right, and then what I would do is I would factor out a common x minus 4, giving me 2x minus 8 times x minus 4 minus 2x squared minus 8x plus 12 all over x minus 4. Whoops, I'm sorry, back up here it should have been x minus 4 to the 4th because it was squared and squared again. So that would give me the 4th there. So again, one of those x minus 4s is going to cancel, and so I'm going to get x minus 4 cubed down there. And if I multiply out the top, I'm going to get 2x squared minus 16x plus 32 minus 2x squared plus 16x minus 24. And that's going to end up giving me 8 over x minus 4 cubed. And so there we have our second derivative. Of course, we want to know where is our second derivative equal to 0 and where is our second derivative undefined when our original function was defined. Now, interestingly enough, it's never 0 because the numerator is 8. And it's not undefined anywhere that the original function was defined. Remember, 4 was a discontinuity. So what we have here is we don't have any points to put on from the second derivative. So when I go to my chart, there will be one point. This is why I have to put the 4 discontinuity, because things can happen there, and I have to entertain the possibility that something is going on at 4, or changes are happening at 4. So again, if I go to my second derivative here, and I start plugging in numbers, I see that if I put something like 3 less than 4 in, the denominator will be negative, so this whole thing's going to be negative. And if I put in 5, the denominator will be positive. So I do see that the original function f is concave down below 4 and concave up above 4. But realize that 4 is not an inflection point because it's a discontinuity. There is no point 4 on the graph, so it can't be an inflection point. The concavity changes there, but it's not a point on the graph. So, but it is important to know the different concavity there. So now I'm going to go ahead and put all this information together on my sketch here. All right. So, what did we know? We knew that we had a y-intercept at 0, -3. So, I'm going to put that in. All right. And we saw that we have a horizontal asymptote at x equals 4. So I'm going to put that in. Okay. And then we saw we had a couple of relative extrema. We had a 2, -2 point. So 2, -2 right there as a relative maximum, and we had a 6, 6 point. So let me get that in. Okay, so 6, 6 appears to be about there. All right, let me extend this up a little bit in case I need more. All right, and so we said this was a relative max, so it's topping out there. This was a relative min, it's bottoming out there. All right, so then how does the rest of this work? Well, let's take a look. Our concavity tells us a lot. It's concave down below 4 and concave up above 4. So this whole area less than 4 has to be concave down. Well, that makes sense because this has to go through there and then keep going down. In fact, we found that the limit as x goes to infinity is -infinity, and that's what that is saying. And then it has to stay concave down over here and head towards that asymptote. Let me fix that. Like this. All right. On the other side, it's similar. It has to head towards this asymptote here. Extend that asymptote. And then it has to head off to positive infinity and keep its concave up. Oops, I didn't want that like that. And head off like that. So that's the graph there. Now, if you're interested, there actually is another type of asymptote. It's a slant asymptote in here that actually goes somewhere in here. Now, we're not going to look at the slant asymptotes, but there are these asymptotes that the function will approach as x goes to infinity. They're not vertical or horizontal, but they're slanted, and that's why we call them slant asymptotes. And but I'm just going to get rid of that for now. That's just a side note. Okay, so we end up with this and realize There are no inflection points. We didn't have any from the second derivative analysis because we don't have a change in concavity anywhere except at an asymptote. That's not an inflection point. So here we end up with a very nice graph again, sketch of a graph for this function.